I don't care if you do it with or without a picture. If anybody really wants a picture, I'm happy to give you a fake picture. So you let me know. You can let me know on Zoom if you want a fake picture. You can let me know in the room if you want a fake picture. And I will give you a fake picture. Because my best guess, based on the homework, is that you'll probably get a picture if you're given a question for area. Yep, I got at least one request in the chat for a picture, so I'm going to give a fake picture. I know this thing is a parabola that opens down because of the minus sign in front of the x squared. And that is some kind of a line with a positive slope. So whatever else is going on, it has to look like that. I know who's on top. Always thrown off by the clock being wrong in this room. Not that clock, but the clock up here. It is like hardwired to the internet. I don't understand how the time can be wrong.
It's ready for the hour switch.
It says 12:08. It's slow by 4 minutes. Which is just a really bad amount of time to be slow by. Like it's close enough that it feels right. Super annoying. Since you are here with us in person, I'm guessing that you are in Maud's class?
Yes.
Okay. Yeah. Yeah, you're gonna need that to come up with upper and lower bounds. Oh, you totally can divide by -1. Yeah. I like to do that too because my brain is not capable of factoring with the minus sign in front of the x squared. Other people are better at that than I am. I have solutions. But it does factor. I did give us something that factors for sure. But I've seen a couple different answers as I walk around with the factoring. And since I tried to do it in my head, I'm not sure which one is right. So maybe I'll do that first step, and then I will let you all set up the integral and try to do the integral. But if I need to find the points of intersection, I'm going to set those two things equal to each other. And I'll show you how I deal with that minus sign in front of the x squared. I know that I need a 0 on one side or the other. And I would push everything to the right-hand side so that I don't have a minus in front of my x squared. It's also fine to do everything to the left and then deal with the minus sign. We'll have the same answer in the end. But I would get a 0 over here by adding the x squared and then subtracting the 6x. But notice that should be the same thing that you got if you just dealt with the minus sign kind of after the fact, either by dividing it or factoring it out. This should factor, but if it didn't factor neatly for you, you can always use quadratic formulas. I think that should be an x minus 1, x minus 2 in terms of the factoring. So now if nothing else, partial credit wise, I know my limits are from 0 to 2 on the integral. But I'm going to give you all a little bit more time to set up your integral, find that antiderivative, plug in the endpoints. For the purposes of the problem, my picture is accurate enough to at least know which function goes on top. Some of the rest of these books I've known for at least whatever before 55. What kind of where we five? Thank you. What brought you in particular? Was there anything?
Yeah, I didn't know there was a workbook class to go
Yeah.
with 16B at the beginning of the class. People were like, oh my God, I can't believe there's no workbook with it. And then my friends were like, oh, I was able to like do this. It's been really helpful.
Okay. I didn't know if there was like anything, or if there was like something specific that you were hoping to work on today. I don't think I can fill 50 minutes with midpoint rule. So if there's anything you want more practice with, let me know to make up more problems. It's just my warm up for us.
If you could go over like integrated trigonometric functions.
Oh yeah, always popular in this room. Yeah. For sure. We can keep sprinkling in some trig. I can use trig as an excuse to do midpoint rule. So there is a question in the chat on Zoom that I do think is definitely worth looking at. So the reason that I knew that the parabola was going to be on top and the line was going to be on the bottom, specifically whenever we have a parabola and a line, the same kind of thing is going to happen. I just need to know if the parabola points up or down. So if I know that my parabola, get this off the screen for a second, but if I know that the parabola is concave down, then no matter where I put the line, the parabola is on top. And if I know that the parabola is concave up, then no matter where I put the line, whether the slope is negative or the slope is positive, doesn't matter, the line's always going to be on top. So I don't actually need to like spend a lot of time finding the x and y intercepts or the vertex of the parabola or something. In the context of 16b, I just need to know who's on top. And it's enough to know which way the parabola points to figure out who's on top. Hopefully that was helpful. Which means I know that my parabola is on top. So my setup for the integral here would look like 6x minus x squared minus 3x plus 2. We have a choice. Either we can combine the stuff inside of the integral, or we can break this apart as separate integrals. Either one is fine. We'll get the same answer both ways. I'm going to combine stuff just because then it's fewer parts that I have to plug numbers into later. So if I do this subtraction, the 6x minus 3x would leave me with a 3x. And then I've got that minus x squared and a minus 2. If you didn't do it this way, don't worry about it. If you broke it apart into pieces, it's totally fine. We should get the same final answer in the end. Finding that antiderivative, now I'm definitely going to look at this as 3 separate pieces, but all of these are like that general power rule. I'm going to add 1 to the exponent, divide by the new exponent. Add 1 to the exponent, divide by the new exponent. And the antiderivative of -2 is -2x. Notation wise, once I'm done with the antiderivative, we give ourselves a vertical bar, show that we're going to plug in the 2 and then plug in the 1. I wanted to show everybody a little computational trick if you are simplifying your answers here. So I'm going to go ahead and plug in the 2. I'm going to do the math. It's going to work out too nicely maybe to show you what I was going to show you, but it's okay. So if I plug in 2, 2 squared is 4, 3 times 4, I get 12 over 2. 2 cubed is going to give me 8. So I'll have 8 over 3. And then 2 times 2 is 4. When I plug in the 1, I'm going to end up with 3 over 2 minus 1 over 3 minus 2. Since we're not getting a calculator to play with, it's probably fine to just leave it there and not simplify it. But if you wanted to simplify it, one of my suggestions is to not try to get common denominators across everything, to group terms that already have a common denominator. So if I take 12 halves minus 3 halves, then that's 9 halves, just kind of grouping things that are already similar-ish. I'm going to have -8/3 minus -1/3. And minus, yeah, so like positive, so I'll end up with -7/3. And then -4 minus -2 is going to give me -2. So even if I did want to get common denominators, at least now I'm only dealing with a couple pieces and not like a ton of pieces that I'm trying to get common denominators on. I don't think it's worth our time. I personally would just leave it here. Good times. I'm going to pause in case there are questions. Not seeing any in the chat, but I'm going to give it a minute. And then one of the questions that I got in office hours yesterday, I will get to in a second, but there is a question in the chat. So if the x-axis is one of our bounds, do we have fewer steps to take? Probably. So it kind of depends how the question is written. But let's say that I'm going to make our lives real easy. And here is y equals x cubed. And let's say that I was asking to find the area bound between y equals x cubed, the x-axis, x equals 1, and x equals 3. Well, here we get to skip lots of steps because I've already given us that our bounds are going from 1 to 3. And then because it's the x-axis, I don't really have like a top function minus a bottom function. Or if you want to keep it as a top function minus a bottom function, then the x-axis is secretly the function y equals 0, which means that if you were to set up your integration, you could write this as your top function of x cubed minus your bottom function of 0. But we don't usually. So in that sense, yes, we could definitely sort of skip that step of having the extra piece to subtract off. Yeah.
Can you explain the y equals 0 every time?
Oh, like how the x-axis is the line y equals 0. So it always felt counterintuitive to me, right? But if we just think about what some of the points on the axis are, like if I were to label these, so if I label our x-intercepts, we're always labeling that as like a number, comma, 0. And out here, that might be like 8, comma, 0. But no matter what point I'm on, the y value is always 0. So the way that we write that equation is to write it as y equals 0. Yeah. It's kind of like how any horizontal line is always a y equals. And I think it's more clear when it's equal to like anything other than 0. But when it's 0, we just have to remember that we're talking about the x-axis. Yeah. Okay. So what I was going to say is that one of the questions that I got asked in office hours was basically, when do we use the midpoint rule? And my response is when someone explicitly asks you to use the midpoint rule. Now, from a like mathematician-y perspective, we use the midpoint rule or any other integration approximating tool when we have something that we can't integrate. But usually the functions that we can't integrate are also terrible to plug numbers into, which is why most of the questions in the book are really things that we ought to just integrate because they're trying to make the numbers easier for you to plug things in. In the real world, we're using these integration estimation tools for stuff that is too complicated for us to integrate. So let's talk midpoint rule, do a couple examples, and I'll show you a few things that look simple, but actually we don't have the tools to integrate. So this is getting back to where we started all this integration stuff, which is approximating things with areas of rectangles. It's just the midpoint rule is giving us a really specific way to take those rectangles. In general, these problems are going to ask you to approximate or estimate. We're either going to be given some sort of area or an integral. I'm going to go ahead and give us a definite integral here. And let's say that I wanted to estimate the integral from 1 to 3 of, oh, how about, there was a request for some trig, throwing it all together. We're going to make that pi to 3 pi. And we're going to integrate cosine. I'm going to keep it pretty simple on this first one. Cosine of x over 2 dx. The other thing that we're going to have to be given for a midpoint rule problem is the n value, or the number of rectangles we're trying to break this into. I'm going to choose n equals 4. Now our textbook actually is going to give us a couple of different formulas for estimating areas. The only one we've seen so far is midpoint. Eventually, we're going to add to that trapezoid rule and Simpson's rule. Simpson's rule is actually our best estimate for the integrals. But for now, the only thing we've got is midpoint. Well, what this question is saying is, I'll be Desmos for us today. I'll sketch this graph. What this integral is saying is that we're taking a look at cosine of pi over 2. Cosine starts up at the top and normally completes a cycle in 2 pi, but I have changed the period here So 2 pi divided by 1/2 is 4 pi. So I've actually changed our period so that it ends over here at 4 pi. That means 2 pi is in the middle. That's a pi, and that is a 3 pi. So the actual area we're looking at here is all of this part down here. But what the midpoint rule is going to do is, first of all, since it says n equals 4, I'm going to break this into 4 pieces. All the pieces are going to be equal in width. So that means that the width of each of those is going to come from looking at the total length of the interval we've got divided by how many pieces we broke it into. So that's 2 pi divided by 4, or pi over 2. So that's how wide each of my rectangles is. Now to get the height, that's where the name midpoint comes into play. That name midpoint tells me that on each of these intervals, I need to find the middle. Honestly, that's the hardest part of these problems, is just finding what values we're supposed to be plugging into the function. I know I threw pies and fractions in the mix, but it's because I figured we might as well practice something a little bit messy. So at the midpoint of each of these intervals, then I'm going to use the function to sample to get my height. Now, I know this question is going to maybe sound weird, but I'm going to ask it anyway. When we're done for this particular problem, what kind of a final answer are we going to get? I don't know how to ask that in a better way. Like I'm doing midpoints. Sorry? Yeah, totally. So we're going to have all these different X values we're plugging in. All of our heights, however, are going to be what sort of numbers?
Oh, you have to plug in values to like the original equation.
Yeah, so we're going to be plugging all of those things into our cosine equation. Yeah, right. So we're going to plug all of these into the cosine equation. There are going to be some bad fractions. Agreed. Here's the thing. With a lot of these midpoint rule problems, unless you keep the question super, super simple, the numbers get real messy in a hurry. I don't think he intends for you to do that homework without a calculator. So if you haven't taken a look at homework 13 yet, I genuinely do not believe he thinks you're doing that by hand. I think he wants you to know how to set it up by hand, and then please reach for the calculator, okay? Because they're just gonna get too gross in a hurry. So let's set up so we know what we would plug into the calculator here. Okay, I made my picture really messy. I clogged it up with a lot of stuff. Here's what I actually do. I don't ever draw the graph itself, because the only thing that I really care about is that we're breaking up from pi to 3 pi into 4 pieces. So that's a 2 pi. That's a 3 pi over 2. That's a 5 pi over 2. And now I have to go get my actual midpoint values for those x's. Now there's a formula for getting them. And that formula looks like, well, how do I find the midpoint? That's the same way we would have done it back in 16a. I take the average of the two numbers. So if I want the midpoint of pi and 3 pi over 2, I need to take the average of those two numbers. I would do that by adding them and dividing by 2, which means if I'm going to add these fractions, I probably want them all to have a common denominator first. So I'm going to write that pi as 2 pi over 2. And I'm going to write 2 pi as 4 pi over 2. And I'm going to write 3 pi as 6 pi over 2. Way easier for me to do the math now. So to find the midpoint of 3 pi over 2 and 2 pi over 2, I'm going to add those together and then divide by 2. So that's 5 pi over 2 divided by 2, or 5 pi over 4. Because dividing by 2 is the same as multiplying by 1/2. So I've got 5 pi over 4. Now I have options. I know that the width of each interval is pi over 2, so I can just increment by pi over 2. Or I can keep finding the midpoint of the next two regions. Again, I'm going to say, let's just get a common denominator so we can work with it. Pi over 2 came from 2 pi over 4, so I can increment over by 2 pi over 4. So I would have 7 pi over 4, and then 9 pi over 4, and then 11 pi over 4. And that is the grossest part of any midpoint problem, is figuring out what the x values to plug in are. In terms of the formula for midpoint, it's the same as the formula for the area of a rectangle. The only thing we're doing in that formula is because each of our rectangles has that same width, has that width of pi over 2. We can factor the width out in front and then just stick each of our heights in. And we're going to find the height by plugging each of those midpoint values, which we could think of as x1, x2, x3, x4 in this case, into our function. So I would have cosine of 5 pi over 8 plus cosine of 7 pi over 8 plus cosine of 9 pi over 8 plus cosine of 11 pi over 8. I don't know what any of those values are. Please pick up a calculator if you need to do that. I would argue that this is definitely a case where just doing the integral is way easier than doing the midpoint rule. So just for fun, how about if you try the integral directly? Oh, there's a question about why the pi over 2 in the front again. So this part is like the width of each rectangle. And then these are each of the heights of the rectangles. But since each rectangle has the same width, we go ahead and factor it out in front of the formula. You don't have to do that. You can multiply each of the heights times the width if you want. That's fine too. I know there's kind of a lot going on here. So just so we have less to visually get in the way, I'm going to flip the page and just rewrite the integral for us to practice. But I'll flip back to this if anyone has lingering questions. But we were integrating from pi to 3 pi cosine x over 2 dx. Oh, because the function has an x divided by 2 in it. So like that's my x value is 5 pi over 4, but when you divide that by 2, it'll be 5 pi over 8. With a U substitution or from memorizing formula stuff? Memorizing? Okay. What? Totally. So we're gonna have to do both, but but I don't actually need a U substitution on this if the integral that we memorize is that the integral of cosine of a number times x dx is equal to 1 over that number times sine of the number times x plus a constant. So one of the things that I really miss about physical textbooks is that when we had a physical textbook for your calculus book, the back cover had the most generalized formulas, which included constants. I'm sure it's somewhere in an appendix in the current textbook. It's just harder for me to find stuff in the digital text. But we'll get the same thing by a U substitution. Personally, I would be thinking about it like this. So, but for completeness, let's also try it as a U substitution, just for fun. So when I look at this, because it's not just a cosine x, there's something else in there. I'm going to let that something else be equal to U, which means that my du would be 1/2 dx. I don't have the 1/2. So 2 du is what I would substitute for dx. We have a choice to make. Do we convert the limits? Or do we plug our x's back in at the end? Our book does both. Okay. It's like our book presents both options, so just wasn't sure what people prefer. So we'll roll with this. So when I make those substitutions, I end up with cosine of u and 2 du. And that's what I'm integrating, which is going to lead me to 2 sine of u. And I don't need the plus c part because we're going to have limits of integration. And I'm going to write these as x is going to pi and x is going to 3 pi, because it is important to remember that we have to plug those back in if we're going to use the 3 pi and the pi. So I'd have 2 sine of x over 2 from pi to 3 pi. So 2 sine of 3 pi over 2 minus 2 sine of pi over 2. And I actually give us really nice numbers for the integral. So I would finish this off because sine of 3 pi over 2 is equal to -1. So I'd have 2 times -1 minus, and sine of pi over 2 is equal to +1. So I've got -2 minus another -2, and I would get -4. Which, by the way, if we think about what the graph looks like, totally makes sense that we got a negative number. Because if I flip back to my graph over here, all of our area, sorry, I'm just trying to show both things at the same time. It's not going so well, whatever. I'll give up trying to show 2 things at once. All of our area was down here below the axis, which means when we do that integral, we expect the value to be negative. Okay. What do you all want to do? We got about 15 minutes left. Messy trig stuff, more midpoint rule. I mean, genuinely, the hardest part about the midpoint rule is figuring out what the X values are to plug in. So I'm even happy to do one of the ones that is on the homework if anyone hasn't done those yet and at least wants to get as far as figuring out what the X values are. You want to do one? See what you said? Okay. So I had those pulled up. Thought I had those pulled up. I will pull them up quickly. Should we look at the messiest one or the nicest one? They're all n equals 10. The nicest one. Okay, so I think the nicest one that he gave is probably the first one. So for all of these, we're letting n equal 10. And the first one, he gives us the interval from 1 to 6 of x squared dx. So again, let me just say, no one is ever using midpoint rule to do that. That is like going to take us a minute or less to solve. I am looking at 1/3 x cubed from 1 to 6. I'm plugging in the 6. I'm subtracting, plugging off the 1. Done. The reason he's doing it is because it's going to be easy for us to plug numbers into. So it's just about practice and getting used to the formula. Okay, so if we're going to practice and get used to the formula, I'm going to give us the space here. We're going from 1 to 6, and we can break that into 10 pieces. You don't really have to draw it out. I just kind of like to. So first, we have to figure out what the width of each of those rectangles is going to be. So I'm going to have 6 minus 1 over 10. So it's 5 over 10 or 1/2. So you all tell me fractions or decimals, doesn't matter. You pick. If we're going, let's go fractions because I heard it first. So that's a 1/2. So the first thing that I would do if I'm dealing with fractions is I want these things to have that same denominator. So I'm going to switch my 1 to be a 2 over 2. And I'm going to switch my 6 to be a 12 over 2. Because now I could just count over. So 2 over 2, I'm moving by 1/2. So 3 over 2, 4 over 2, 5 over 2, 6 over 2, 7 over 2. Let's see if I counted right. 8 over 2, 9 over 2, 10 over 2, 11 over 2. Sweet, I counted right. We got back to where we started. But those are not the values that we're going to use to plug into the function, because we actually need the midpoint for each of those intervals. So if I look at the 3/2 and the 2/2, and I were finding the midpoint, I'd do 3 over 2. I don't know why I put the 3 in front. Sorry, it's weird. 3 over 2 plus 2 over 2 all over 2. So that's 5 over 2 over 2, which is 5 over 4. So the first x value we would use is 5 over 4. And now I know that the width is 1 over 2, but I want to change that to have a common denominator. So I'm going to call that width 2 over 4. So that I can add by 2/4 to get all the x values we need. To be honest, Like if I'm trying to save myself from writing for the next hour, now that I know where I'm starting and that I'm incrementing by 2/4, I'm like popping that straight into the formula because I don't want to have to write this a million times. So I'm going to take my width, which was 1/2, and then I'm going to just start popping those x values in to my function. So I'd have 5/4 squared. And then my next one is going to increment by 2/4. So I'll be at 7/4 squared, increment by another 2/4, and another 2/4, and another 2/4. And then just make sure you stop after you've done 10 of these. Nine. Whoa, I had just enough space on my paper. Again, there is no chance that he thinks you're doing that by hand. I promise. He does not think that you're doing 17 squared divided by 16 without a calculator. In fact, this is probably fastest done in Excel, but totally up to you how you want to get through it. It's a little bit gross, but it's not mathematically hard. It's just arithmetically gross. Now, there is a reason that on the homework, he asks you to compare to the value of the integral. And by the way, even on that, I'd throw that in a calculator. But he doesn't ask you to do that for the third problem, because the third problem is actually something we can't integrate. The third problem is the only one that I would actually have to use the midpoint rule on. These other two, I'll just do this way. Sorry. Yeah, so the last one is the only one that we, oh, you mean like tried to did it all the way out with the grossness of plugging stuff in?
No, I did that for number 2.
Yeah. Okay. Questions about fraction math? Because that's kind of what this part comes down to. Okay, we got 7 minutes left. What are we doing, folks? Fun with trig? Okay. Can I make it slightly messy trig? Not super messy, because I don't know if you've looked ahead to the syllabus, but we're going to do, I'm trying to remember how he phrased it, complicated quiz and trig integrals. Is anyone else as fascinated by his phrasing on the syllabus as I am? No?
Like that too. Yeah.
Oh, yeah. Yeah, he had some cute little phrase for it. Yes, we'll be doing well, you have done simple trig integrals, and then we will move on to trig integrals. I'm not entirely clear on what the difference is. My guess is, right. And so my guess is the second set of trig integrals will be things that involve more complicated U substitutions and maybe some trig identities. That's my guess of what we're going to get in what he's calling the not simple. Yeah. So let's just do a few trig integrals. I'm going to keep them fairly simple. So let's say I had x squared secant of x cubed, tangent of x cubed. Sure. Let's do this. I'm going to do a few different variations on this same problem. But if that's the problem that I have, for sure, I'm looking at that and going, I've got x cubes and the derivative of x cubed is x squared. So I know there's a u substitution that's going to help me out here. So I might as well do that piece of it. So what I'm looking at isn't quite so messy. And if I let u be equal to x cubed, then du will be 3x squared dx, which makes 1/3 du x squared dx, which I have. I have the x squared and I've got the dx. When I use my vocabulary list to make my translation, I've got 1/3 secant u tangent u du. And now comes the place where, yep, we just have to memorize stuff. So when we see secant u times tangent u, we just have to know, oh, I know whose derivative that is. That's the derivative of secant. And I've got 1/3 secant of u plus a constant. Don't forget about that pesky constant. And then I want to put my final answer back into x's because I like to get all my points on a problem whenever I can. Now, if I change this problem up slightly, so that it says x squared secant squared x cubed tangent x cubed dx. So I just did one little thing, but that one little thing made a very large difference in how I'm going to approach this. Honestly, I'm probably still going to look at that and see the x cubed and the x squared and go, let me do that u substitution so what I'm looking at looks a little bit better. So I would probably start with that same u substitution. It's not the only option here. I'll show you our other option in a second if I don't run out of time on the real clock. But that would make this secant squared u tangent of u du. And that's when I would look at that and go, oh, that isn't somebody's derivative, but somebody's derivative is hiding in the problem. Whose derivative is hiding in the problem? Secant squared is somebody's derivative. So yeah, so secant squared is the derivative of tangent, which means we could kind of do a second u substitution. And sometimes when we do the second u substitution, we call it w, because it's a double u substitution. So I would call w tangent of u, and then dw would be that secant squared u du. So now this would be 1/3 times the integral of u du. Sorry, w dw. Because the tangent of u would be my w. And the secant squared u du would be my dw. So if I integrate that, I'd have 1/3 times w squared over 2 plus a constant. And then I would plug in what my w was and get 1/6 tangent squared u plus a constant. And then I would plug in what my u was and get 1/6 tangent squared of x cubed plus a constant. I am out of time for today. So I'm going to stop my recording.